In this video, we're going to learn how records work in C#. Records are a really useful technique that I don't see used in a lot of the projects that I regularly work on. They can make your code cleaner and easier to understand, and also lead to less bugs and having to write boilerplate code. By knowing how to use records properly, you'll learn a lot about equality and immutability, which are two very important concepts for a developer to know that regularly come up in job interviews. First, we're going to discuss equality and immutability and look at a few examples. If these are two concepts that you understand quite well, then you can skip the first two sections of this video. There are two main types of equality in C#. Reference equality, which is also called identity, and value equality, which is also called equivalence. Two objects have reference equality if they are the same object, i.e. they both point to the same location in memory, and as a result everything about them is identical. They are the same object, they have the same type, same values, same fields. Value-based equality means that two objects have the same value. For example, if you have two integers like we have defined here, even though they both point to different locations in memory, since they both have the same value, this will return true. Let's have a look at the equality example that I've set up here. First, I've created a class called pointClass with three coordinates, x, y, and z. And by default, a class will use reference-based equality. Next, I've defined a struct with the same three x, y, z coordinates. And since a struct is a value type, by default, it will use value-based equality. I've then created two instances of the point class, and both instances use the same values for x, same values for y, and same values for z. I've then created two instances of the struct, and I've done the same thing with the coordinates. Let's run this code and take a quick look. So we can see on line 20, I've used the built-in equals function to compare for equality. And you can see that point class 1, and here we've got point class 2, and they are not equal because even though they have the same values, this equals method is using reference-based equality. Now, how could we make this expression return true? Well, we'd have to take one of the two variables that we've defined here and make sure they both point to the same instance of the class. So here I've taken point class 2 and made it equal to point class 1. So now they both point to this object in memory. I've then tested for equality. Now, these two functions essentially do the same thing in this instance, and you can see that this returns true. I've then done the same for the two point structs that I created here, except here the equals method is using value-based equality, and you can see they're both equal because they share all the same values. They all have the same values. Next, I want to discuss where these two different types of equality come from. It involves the implementation of the equals method. A reference type will inherit its equals method from system.object, and a value type will inherit its equals method from system.valueType. If we peek the definition, we can see this class is inheriting from the object class, and the equals method will return true if the specified object is equal to the current object, i.e. they are the same object in memory. If we peek the definition of the value type, we can see struct has inherited from the value type class, and the equals method returns true if the object and this instance are the same type and represent the same value, otherwise false. So in this instance, it's the value and the type that are important, not the memory location. Now, I also want to discuss two other examples of an integer and a string. So I've created two ints and two strings for comparison here, and I've used the double equals and the dot equals methods for comparison. Now, the dot equals method and the double equals operator are not always the same, as you could provide your own implementations of them, which could be entirely different. So this is something that you need to watch out for. But in this instance, they will both return the same values. So if we run this code and take a look, we can see both of these integers have the value 1 in, and they both return equal. If we peek the definition of this, we can see the equals method is inherited from the int32 class, which these integers are an instance of. And the equals method returns true if the object has the same value as the instance, so it's the value that's important. Now we'll take a look at the comparison of two strings. A string is a good example because a string is a reference type, but it uses value-based equality. So not all reference type are going to use reference-based equality, and equally any reference type could have its own implementation of equality, which is different. Here we've created two strings, both with the same 3 characters in. And if we check for equality, you can see they're both equal. If we take a peek at the definition of equals, we can see that strings get their equals method from the string class, and equality is based on having the same value. Looking at this string example, you might still think that it is using reference-based equality. Let's say, for example, that we have the string ABC, and that is stored at a location in memory, and we both have C and D both pointing to that memory location. Then, when we check for equality, of course it will return true, as both C and D are pointing to the same object. If C and D were actually pointing to different locations in memory, this would return false. That's something we can test using string.copy. If we create a new string, E, and we use string.copy to create a copy, so now we know that both D and E contain the string ABC, and we also know that they're pointing to different memory locations. We then check for equality. We can see that E and D are both equal because the string type uses value-based equality. I've also created an example that we can take a look at where we take a class that uses reference-based equality and we modify the equals method and the double equals method and the hash code so that it will use value-based equality. First, I've created a class called point3d, and in the first instance, I've not modified the equals method. Let's run this code and take a quick look. I've created 2 instances of the point3d class, and they both have the same x, y, and z coordinates. And because they're using reference equality, both the equality checks we've done here are returning false. I also briefly want to mention the hash code. Now, a hash code is used to uniquely identify items in constant time for things like dictionaries. So when you want to retrieve an object from your dictionary, the reason it can be done so quickly is because the dictionary has a hash table which maps the hash code of each object to the object, so they can be retrieved quickly. And under value-based equality, if we had 2 points where x, y, and z were the same, we would want them to have the same hash code. But since this class is using reference-based equality, we can see the hash codes are different. Let's modify our point3d class so that it uses value-based equality, which I've done here. So we've got a class called point3d. It has 3 coordinates, like with the other class. And the most important thing I want to show you is the equals method. So these 2 checks here are just used to quickly return a value. So for example, if the object that we're comparing to is null, then obviously we just want to return false. And if they're the same object, then we want to return true because they're the same object. Of course, they're equal. And then lastly is the actual equality check, similar to the equality check in system.valueType. So if the z values are the same, the x values are the same, and the y values are the same, then we want our equality check to return true. We then use this equals method to override the system.object equals method. And we also override the equals operator and the not equals operator to again use the equals method that we created. And lastly, we modify the hash code to be based on the 3 coordinates. So by overriding this method, 2 instances of the point3d class will have the same hash code as long as x is the same as the x, the y is the same as the y, and the z is the same as the z. Now, if we run this code, and we take a look using the modified version of the point3d class, we can see that both the equality checks now return true and the hash codes are both the same. The next thing we're going to take a look at is immutability. Now, immutability means that something cannot change. If a field in a class is immutable, then it cannot be modified once it has been initialized. This is a useful property in computer programming. For example, it can help avoid bugs. If you know a value isn't going to change once it's been initialized, then you're not going to run into unexpected behavior later on in your code where the value has changed. You also have to write less boilerplate code, less defensive code, because you know that these values aren't going to change, so you don't need to write code to check that they haven't changed or check that they're in the right state. And also, immutability helps with writing thread-safe code. If you have two threads, you don't have to worry that one of them is going to change that one of the values and lead to a race condition. Here I've created an example of a mutable and immutable fields. First, we have a class called mutable.2d, and we just have two xy coordinates with a get and a set. You can see on line 13, I've created an instance of mutable.2d. I've set the x value to 1 and the y value to 2. And then later in the code, I've tried to change these two values. The compiler doesn't give me an error, and if I try to run this code, it will work. Then I've created a class called immutable.2d. And the way to make your field immutable is by changing the set to init. The init keyword will put a restriction on the x value such that it can only be set when the object is initialized. If we take a look at the example here, I've created an instance of immutable.2d. I've set x to 1 and I've set y to 2. And then later on in the code, if I try to change those values, the compiler gives me an error and this code won't run. If we take a look at the error, it says x can only be assigned in an object initializer. So that's how you create immutable properties. Now that we've gone over equality and immutability, we can take a look at records. Now, what is a record? So a record can be a reference type or a value type, but the most important feature is that records use value-based equality. So let's say we're creating a class and we want it to use value-based equality. Instead of having to write all of this code that we looked at here, where we override the equals method from system.object, and we have to write a custom equals method, which makes sure the z and the z are equal, the x and the x are equal, the y and the y are equal, and provide this custom hashcode implementation, a custom equals implementation, and a custom not equals implementation. We can simply just use a record. Records also provide convenient syntax for creation, immutability, and also outputting the values within your record to string. If you're somebody that works on business applications, then I think records can be used for things like data transfer object or a search parameters class. And if you work with data science, then records are definitely useful for data applications. So let's take a look at how to define a record. I said that a record can be a reference type or a value type. To define a reference type record, we just have to write record. But we could also write record class to make it clear that it's a reference type. And then, as with a class definition, we can provide the constructor and we can provide the values. And you can see here I've made it immutable by providing the init keyword. However, there is a more convenient syntax called the positional syntax, which we can see here on line 39. And just by writing this one line, we get a record that is equivalent to all of this code here. So it's a really concise syntax. If we want to define a value type record, then we simply write record struct. And then again, we can define our constructor, we can define the fields, and we can use the init keyword if we want them to be immutable. We can also use the positional syntax with value type records we see here on line 54. However, if you want your records to have immutable fields, then when using the positional syntax, you need to add the read-only keyword. Of course, you could also make your records mutable, but you would have to use this syntax or this syntax. You would just change the init to set or private set, depending on your use case. Let's take a look at an example of using records. So here I've created two instances of the person record, both with the same first name and the same last name. We run this and take a look. First, we can see that they're equal because the record uses value-based equality. And as I said, a record overrides the toString method. So if we take a look at this toString output, we can see all of the values of the fields within the record, which is very convenient for data science applications and also logging applications. Now, one of the problems with immutability comes when we actually want to modify one of the fields that we've made immutable. For example, let's say we had this instance of the person class and we wanted to change the first name. Well, since the first name is immutable, we would have to create a new instance of this class with the same last name but a modified first name. sort of like how you can see here on lines 28 to 29. I've created a new person. I've given it a new first name, but I've used the last name from the person1 instance. A convenient way of doing that, instead of having to write it like this, you can use the with keyword. So we say person3 is equal to person1 with a different first name. If we look at the toString output of person3, you can see we've got the last name from person1 and we've got the new first name that we provided. The last thing I want to look at concerning records involves inheritance and equality. Now, since a record is basically a class that uses value type equality, we can also use things like inheritance. Let's say we have a base record called person, and then we create a teacher record which inherits from the person record, and we also create a student record that inherits from the person record. Now, both the teacher and the student records have a first name, a last name, and a grade. Let's say we create an instance of the teacher record, and we also create an instance of the student record. Now, you might think that since the first name, last name, and grades are the same, and they are both stored in person type records, that they would be equal when we do an equality check between teacher and student. If we run the application and take a look, we can see that the first equality check returns false. And that's because for two records to be equal, the runtime types must be the same. So here we can see the compile time types for both of these instances are person, but the runtime types are teacher and student, so they're different. We don't get equality. If we then create a student with the same first name, last name, and grade, and we do an equality check between this instance and this instance, then you can see we get an output of true because they both have the same runtime type. I'm going to end the video there. Thank you for watching. Please give the video a like if you found it useful. I'm going to be releasing multiple videos in this series, so please follow the channel and look out for those.